What's up, everybody? Welcome to the 6th lecture of trig. Today we're going to be talking more about graphing trig functions. To start off with, I thought it'd be nice to start with tangent of x. So, the graph of tangent of x looks about like this. Everybody say your oohs and ahs. And no, it's an amazing graph, right? So awesome. So, looking at this graph, you might notice a couple things. It looks kind of strange at first. One thing you might notice is we've got all of these dotted lines marked at odd multiples of pi over 2. What are they? Why do they happen? Well, these dotted lines are called asymptotes. They're lines that our function gets really close to, but it never actually touches. So we can, as we're moving from negative pi closer to 0, we will start approaching negative pi over 2, but we'll never actually cross that line. We'll never touch that line. And eventually we get so close to it till something happens and all of a sudden we end up on the opposite side of it. But now, we're no longer positive up here. We're now at negative infinity way the hell down here, and we're moving up. And as we pass 0, we start doing the same thing, but approaching pi over 2. These things, again, are called asymptotes. Asymptotes are lines that your function will approach, but never actually touch. So, what causes them? What are these? Our first clue is in observing that these occur at odd multiples of pi over 2. Okay, what's special about pi over 2? Well, we might look here and we say, all right, well, odd multiples of pi over 2, so when our sine function is 1. That's not helpful at all. But if we look at our cosine function, odd multiples of pi over 2, that's when cosine is 0. And it just so happens that we know tangent is equal to sine over cosine. But we know also that you can never divide by 0. So this has got to be the reason why, right? And it is. The reason why we have these asymptotes is because these are the points where cosine is 0 and you can't divide by 0. Okay? That's convenient. What else do we know? We also know that at multiples of pi, our tangent is 0. Why is that? Well, we can come back to our nice lovely unit circle and we might be able to see that. Notice at 0, y is 0, so sine is 0. We move on through. At an angle of pi, well, sine is 0 again. Move on through. At another angle of pi, so now we're at 2 pi, we've gone all the way around. Sine is 0. We move halfway around again. Sine is still 0. Over and over and over and over again. This always happens at multiples of pi. So again, because tangent of x is equal to sine of x over cosine of x, what we've got is 0 divided by a number. But 0 can't be divided by a number. That's 0. A fraction of 0 is still 0. So every time we have a multiple of pi, tangent's going to be 0. Now let's look at what happens to the rest of it. Notice in this chunk here, we're negative. And then all of a sudden in this chunk here, we're positive, negative, positive, negative, positive. Why does this happen? Well, this happens because what we've got are positive numbers divided by positive numbers, negative numbers divided by positive numbers. My mistake, I said that backwards. Positive numbers divided by negative numbers. Negative numbers divided by negative numbers. And negative numbers divided by positive numbers. So in these two quadrants, tangent's going to be negative, and in these two quadrants, tangent's going to be positive. So we're alternating from positive, negative, and that's what's showing up here. We're also seeing that as we get close to pi over 2, any odd multiple of pi over 2, well, as we get close to those, the magnitude, the size of the number, don't think about the sign, think about the absolute value, just the magnitude of the number. It happens to be the case that the absolute value of sine is a lot larger than the absolute value of cosine. And that makes sense because cosine is getting closer to 0, and sine is getting closer to 1, positive or negative. So having said all of this, let's look at cotangent now. But before we get to cotangent, I want you to take just a second of yourself to actually think about some of these relations and how they might help inform you on what cotangent is going to look like. Now, for cotangent, you might notice it kind of looks like tangent, but shifted over and flipped. There's a reason for that, and we'll talk about that later in the semester. But for now, let's just think about cotangent as it exists. Cotangent, we already know, is equal to cosine over sine. Well, just like with tangent, we had those zeros that we couldn't divide by, and they created asymptotes. We have the same thing happen for cotangent. And notice they happen at every multiple of pi. Okay, well that makes sense, right? Because it corresponds to where sine would be 0. Sine's 0 at 0, pi, 2 pi, 3 pi, 4 pi, so forth and so on forever, right? Similarly, cosine is 0 at odd multiples of pi over 2. So we have these zeros then that occur at odd multiples of pi over 2. We have negative pi over 2, pi over 2, 3 pi over 2, 5 pi over 2, etc., etc., etc. And in general, it's going to follow all the same trends. Notice that just like the cotangent, between 0 and pi over 2, cotangent's positive, and between pi over 2 and pi, cotangent's negative. Again, just like with tangent. And it's for the exact same reason. So having said that, what about cosecant? Well, let me back up for just a second. Having said that, there's something else I wanted to point out. With the other trig functions, I've said that they're 2 pi periodic, right? Well, notice here, not only does cotangent repeat itself every 2 pi interval, it repeats itself every pi interval. We go from 0 to pi, from pi to 2 pi, so forth and so on. It's because cotangent and tangent both are pi periodic. They repeat themselves every pi interval. Now, having said that, let's go check out cosecant and secant. Now for cosecant and secant, instead of telling you which graph belongs to which function, I thought it best if we work it out by looking at one of the graphs. So in this case, what we've got is all these U's and N looking graphs. And then we've got these asymptotes at multiples of pi. And we have these two vertical lines at y equal to 1 and y equal to -1 that our function touches exactly once every interval, right? So every time it makes one of these U or N type shapes is what I'm trying to say. All right, well, using this information, we already have a big tip-off, right? Just look at the asymptotes. We have an asymptote at -pi, at pi, 2 pi, and 3 pi. Like I said, multiples of pi. Well, we know cosecant and secant are 1 over sine or cosine, right? So this must mean that in order for us to have asymptotes at pi, at -pi, pi, 2 pi, 3 pi, so forth and so on, well, our function must be 0. Whatever our denominator is, it must be 0 at those points. Well, there's only one function, one of our trig functions, that is 0 at multiples of pi, and that's sine. So because sine is 0 at multiples of pi, we know this is 1 over sine x, which is equal to cosecant of x. So the cosecant of x is going to be the graph that looks like a bunch of u's and n's, where the first u is bounded between x equal to 0 and x equal to pi. Notice this, unlike our cotangent and tangent, this is 2 pi periodic. And it's 2 pi periodic because we start at 0, and at 2 pi, we begin to repeat ourselves. So it has a periodicity of 2 pi. Having said that, let's look at secant now. So for the graph of secant, it pretty much looks like the graph of cosecant, right? Just shift it over. That's pretty much the idea. In the same way that cosine and sine look pretty much the same, just shifted, secant and cosecant are going to look the same, just shifted. Notice with secant is equal to 1 when x is equal to 0, just like cosine is equal to 1 when x is equal to 0. Well, this makes sense because secant is 1 divided by cosine of x. So 1 divided by 1, all right, we're going to get 1, cool. Also notice we have asymptotes at -pi over 2, pi over 2, 3 pi over 2, and 5 pi over 2. Well, those correspond to our zeros of cosine. So everything more or less shakes out, right? We're going to be equal to 1 at even multiples of pi. We're going to be equal to -1 at odd multiples of pi. So that shakes out. And really, this is all there is to it. Just knowing these general forms of what the graphs are going to look like for sine, cosine, tangent, cotangent, secant, and cosecant. Having said that, let's look at a couple other graphs. So now that we've talked about all of the different trig functions, let's play with them. And let's start by trying to graph x times cosine of x. Well, to do that, let's think back to the graph of cosine of x. The graph of cosine of x, we know, is bounded between 1 and -1. Okay, so if I wanted, I could write that as an inequality. Say, I know that -1 is less than or equal to cosine of x, which is less than or equal to 1. Well, what I want is to find the graph of x times cosine of x, right? And if I were to multiply all of this by x, wouldn't I get x times cosine of x in there? Yeah, right? So let's write that out. If we multiply all of this by x, what we're going to have is negative x less than or equal to x times the cosine of x less than or equal to x. So this tells us something. This tells us that x times cosine of x is going to be stuck between the equations negative x and x in the exact same way that cosine is stuck between 1 or -1 and 1. Well, if that's the case, why don't I just go ahead and draw the lines y equal to x and y equal to negative x up here? Seems fair enough, right? So this is the line x equal to y. And this is the line negative x equal to y. Okay. So let's think now about how cosine relates to these boundaries. We know that cosine, again, it's like 12:30, so I might say things funny now. But we know that cosine touches the line y equal to 1 and y equal to -1 at multiples of pi. So, since all we did was multiply through by x, we know the same thing's going to happen here. That our cosine of x is going to be stretched to touch these lines at intervals of pi. Okay, so knowing that, looking at that, what else might we know? Let's hold on to that for a second. We also know that cosine is equal to 0 at odd multiples of pi over 2. So forth, so on. So we know we're going to go through 0 at these odd multiples of pi over 2. And we know at multiples of pi, we're going to touch these purple lines. So how are we going to use all of this now? Well, we can start by saying what we know. We know that cosine at pi is -1. -1 times x is -x. Well, we just said x was pi, though. We're talking about this point right here, right? Well, if that's the case, then our function must touch right here. Now, in the case where x is equal to -pi, again, we know cosine is -1. -1 times x negative x. The negative x, but x is negative pi. And the negative of a negative value is positive. So we must be not at negative pi, but at pi. In the case of negative 2 pi, cosine is 1. 1 times 2 pi, or times negative 2 pi, I mean to say, is going to be negative 2 pi. Cosine of 2 pi is 1. 1 times 2 pi is going to be 2 pi. And we already know we're going to go through the zeros. So let's sketch this. It's going to look something like this. Kind of cool, right? So what happens if we use other polynomial functions? What if we used x squared? What if we used an exponential like e to the x? Well, let's look at that. Let's look at x squared times sine next. All right, so for this last example, we want to find the graph of x squared times sine x. And to begin, let's look at the graph of sine x. Well, we know this graph of sine x looks something like this, right? And we know that sine x is bounded between 1 and negative 1. So let's write that inequality. Negative 1 is less than or equal to sine x, which is less than or equal to 1. Well, sine x is like x squared, or what I mean to say is x squared sine x is like multiplying all of this by x squared. So let's do that really quick. When we do that, we get negative x squared is less than or equal to x squared sine x is less than or equal to x squared. So what this means is our function x squared sine x is going to be bounded between x squared and negative x squared in the same way that sine is bounded between negative 1 and 1. So let's draw that up here. X squared looks something like this. It's a parabola. So this is x squared equal to y. This means that negative x squared is the mirror image, so it's just flipped. So this is negative x squared equal to y. Now, sometimes it helps to keep a table with what we're about to do next. We want to find out when x squared sine x touches these lines. Okay? To do that, let's spread out this table. That'll be all right. Okay. When x is equal to 0, sine is equal to 0. 0, 0. When x is equal to pi over 2, sine is equal to 1. Pi over 2, 1. When x is equal to pi, sine is equal to 0. Pi, 0. When x is equal to 3 pi over 2, sine is equal to negative 1. When x is equal to 2 pi, sine is equal to 0. And we know this is an odd function, so for negative values of x, the sign of this flips, right? It's just the mirror image across the y-axis. So this will be enough for us. Okay. At 0, we have 0. Sine of 0 is 0 times 0 squared, 0. At pi over 2, sine is 1, so sine of pi over 2, 1, times pi over 2 squared. Well, that's just going to be pi over 2 squared. Okay? That's up here. That touches the purple line to the top. At pi, sine is 0, so 0 times pi, still 0. We're right here. At negative 3 pi over 2, sine is negative 1. So we have negative 1 times 3 pi over 2, the quantity squared, right? So we're squaring this and multiplying it by negative 1. All right. Well, that means we're going to be down here at 9 over 4 times pi squared. And at 2 pi, we're at 0. So we're right back up here. And now I said before that this is the mirror image, right? Because sine is odd. Whenever we have an odd function, it's just going to be the mirror image, right? Any positive x value that is over here, if we want to find out what the negative x value is going to give us, well, it's just the negative y. That's convenient. So, anything over here that was positive, it's going to be negative over here. If then that was negative over here, it's going to be positive over here. Convenient. So, since we've already found all of our zeros, and we found all of our values for 1 and negative 1, right? We can just go ahead and put everything up here. That's nice. So 0 being 0, of course. Positive value turns into a negative value. 0 being 0, of course. Negative value is going to turn into a positive value. And then, of course, 0 being 0 again. So now let's sketch this out. This is going to look something like this. It's going to look something like this. We don't have to be perfect. So long as I can tell what you're trying to sketch, we're good. And really, this is all I've got for y'all. Having said that, I would like for y'all to take the time and try to graph. Let me erase some of this really quick. I'd like for y'all to try and graph x cubed times cosine of x and x cubed times sine of x. Try to graph the two of those, see what you come up with. In the meantime, if you have any questions, by all means, feel free to shoot me an email. Yeah, have a good one, everybody.